Hello 108 class, Mr. McCue here. Welcome to our very first talking class note videos. We're going to start off the semester with section 1.1 here. Let me get my toolbar going. Sorry about that. Okay, so we're going to go ahead and talk about basic concepts here today, section 1.1. And we're going to work on page 1 on this video. So when you look for the file names, just keep in mind that it'll say 108 space 1.1 space or underscore P1 for page 1. So I will do one video per page, so to allow you to open them up and view them for just a few minutes at a time. Okay, so let's get started here. Another little tidbit to tell you guys real quick is that when you see any number with a circle around it, that corresponds to an objective that's in the book, so you can kind of follow along. So save time on my notes, instead of writing the word objective, I just put the number 1 and circle it. So we're going to talk about set notations here. Set notation is a way to describe a set and also use brackets to list the elements in there. So as you can see, a set can be a collection of elements or numbers. Brackets, fancy brackets, are used to enclose the elements, and a couple examples here would be a finite set means there's a limited number. You could talk about the first 3 counting numbers, give yourself a bracket and list them 1, 2, 3, and stop. Does not go on forever because we've chosen to only talk about the first 3 numbers. Okay, what you're probably used to thinking more of infinite sets, which means the numbers go on forever. And the first one that jumps it all going here are natural numbers or counting numbers. We like to use the name them. Mathematicians like to use a capital letter N for natural numbers, and they say they could be set equal to all the elements that start with number 1, comma 2, comma 3, and the 3 dots is a way to signify that they go on forever, because when you start counting, no matter how big of a number you come up with, you can always say plus 1 and you'll have another bigger number. So if I say 45,000, you could say 45,001. And thus natural numbers never end. They go towards what's known as infinity, and then we use this symbol to represent it. Okay, the next set that you might come up with here are whole numbers. Those are natural or counting numbers plus the number 0. So try to keep these in mind. Every semester when you guys start a new math course, we always review these and just think of natural numbers as counting numbers. Whole numbers was when mathematicians realized that if your wallet is empty and you have no money in it, you can't have any dollar bills, so you're at kind of like neutral. And so the W stands for whole numbers, and the brackets are used to contain the elements inside it. Okay, another little key point we want to bring up here is that if you have nothing in your wallet, you could use the empty set, and you would list a bracket on the left side, one on the right side, and nothing in it. This is where you maybe have a description and nothing satisfies that. Sometimes you'll have a solution set and nothing will satisfy it. You can use the null set, and that is like a 0 with a line going through it, kind of like the Greek letter theta. Okay, now the key thing here, and the book mentions this, there are cautions in the book. I encourage you to read your book, look for these red cautions and hints. This is a very well organized textbook. You cannot put the bracket with the theta, the null set, and the bracket. This is wrong. You don't want to do that. Okay, just keep that in mind. Another critical thing we're going to be working with in this semester is called set builder notation. And this is a way to symbolize where you can have a description of a property of a set of numbers that have a condition. You start off with your left bracket and you end it with the right bracket when you describe these. And the way when you read this is it'll give you a variable. It's usually x. You say all of x, and they put the vertical line. You use the word such that. So you want to remember, say all of x such that. That's the easiest way to get through this reading of this symbolic notation here. Then to the right of the vertical line, you're going to have a description, and x has a certain property, such as all the natural numbers, all natural numbers that are less than 10. So you might have that description, and then you're going to go ahead and have a brackets that will describe that. So let me kind of show you an example here that we can work with. We're going to come down here to example 1. It says list the set, all of x such that x is a natural number and is less than 4. Okay, so there's the description of the set builder notation. The elements that satisfy that are the numbers 1, 2, and 3. There are counting numbers and they are all less than 4. If the problem had asked for less than or equal to, we would have squeezed a 4 in like that, if that would have been the problem. Okay, just trying to give you a feel here. Example number 2 says describe the set. Now you're going to go in the opposite direction. Look at these elements that are in the brackets, 1, 3, 5, 7, 9. Ask yourself, what are you dealing with here? Odd counting numbers comes to my mind. And so if you're going to describe that set, you'd give your bracket sign, left bracket, all of x, such that x is, one way they gave it here was the first 5 odd counting numbers. Perhaps you also could have written that as all natural numbers less than 10. Or perhaps you could have said all natural numbers less than or equal to 9 and are odd. I forgot to put the word odd in there since we're talking counting. Okay, so you get the idea, you describe them. Okay, we're going to keep moving here. Objective number 2, talking about our number line. We always start with 0, draw a horizontal line, give yourself tick marks, and we count. Positive numbers always go to the right, negative numbers always go to the left, and the arrows tell you to go on forever towards negative infinity. The arrow going to the right tells you going towards positive infinity. Okay, so this is all symbolic notation. When you actually want to represent those numbers, you go ahead, if I wanted to represent the number 1, I would put a dot right on top of the 1. If I wanted 1 and 3, I would go like that. Okay, so you might be asked to do some graphing of those in my math lab. Wrapping up here this section here, I could be used as a name for integers. Integers include counting numbers 1, 2, 3 and going on forever. Also include the whole number, which is the number 0, and the negative numbers, such as when you go in debt, when you owe somebody $1 for a candy bar, or you owe $2 for a soda, or $3 for a cup of coffee at Moxie Java. That is what integers are. So I always think of integers as your positive and negative counting numbers is how I look at it. A couple other sets we could talk about. Rational numbers are numbers that make sense, and they are numbers that can be written as a fraction. So if you think of a whole number, can that be written as a fraction? 6 can be written as a fraction. Divided by 1 does not change the value of it, so 6 over 1 is an improper fraction, which reduces down to the whole number 6. Okay, 1/4 is already a fraction, is 0.25. Notice the decimal can be written, every decimal can be written as a fraction. To do this real quick, take all the digits to the right of the decimal and divide it by what place you go into, tenths, hundredths. Another way to do that is to put the 1 associated with the decimal and count how many places and add zeros. And of course 25 divided by 100, 25 goes into each of them once, 25 goes into 104, and you've reduced it down. Okay, 1/3 is also a rational number. Decimal equivalent would be 0.3 with a repeating bar above it, or even 0.333 repeating bar, either way, and that represents the fraction 1/3. All rational numbers. Irrational numbers are numbers that do not make sense, and the classic number is the number symbol pi, coming from the circumference of a circle, and the circumference of a circle is equal to pi times the diameter is the definition. If you isolate for pi, divide both sides by d, you'd end up with this: pi equals the circumference divided by the diameter. I find this very interesting because it's nothing but a ratio that the Greek mathematicians started doing measurements and realized no matter how small or how big the circle, that if you took the circumference, which is going around the circle, measure that and measure the distance going through the circle, the diameter, it always turns out to be equal to 3.1415, and it goes on forever and ever and never repeats. I find that amazing, but we have this happening in the universe. Okay, so that's what irrational numbers are. Okay, class, we have done section 1.1, page 1. I will see you for page 2.